Yeah, we're going to need to have page 806 handy, especially the sample space handy. And I know I've already used some highlight colors. It might be best to find some other markers or highlighters or bring in some other way of notating it or recreate the sample space. That's what we'll do. What is the probability of randomly choosing a summer month or a winter month? And we mean the days, 1, 2, 3. It's a whole thing that happened in the summer conversation. So I'm going to specifically circle in pink on my sample space from page 806 the days from a summer month. It's not December. Did you know that? December is technically not like a winter month. Those are fall days. These days are in the winter. So that's January 1st, 2nd, and 3rd. Those are winter days of a winter month. February 1st, 2nd, and 3rd are winter days, and March 1st, 2nd, and 3rd. Those are also winter days. Actually, not that. They are legit winter days, but spring days. Okay, so here we go. I'm highlighting these 9 days because they fit the criteria that they are days from a winter calendar date. So the probability of summer and the probability of winter. Let's bring back this one. Orange. Orange is summer. 1, 2, 3, 4, 5, 6, 7, 8. There are 9 summer days out of 36. And then the probability of winter days, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 winter days out of 36. We could choose for probability day, celebrate it, what, make it be a thing. Okay. The probability of choosing a summer or a winter month. You know, by the addition rule of probability, you're supposed to add the probability of the first thing to the probability of the second thing, and then take away the probability of what they have in common. That's the intersection with and. So before I calculate this, let me go over here on the side and write down P of S and W. Reminder, that upside down like mountain U shape, it's called an intersection, and it's the word and. That just took so long to write down. I'd rather just write this one. Okay. So how many of these days are both summer and winter months? Days. Summer days from a summer month and a winter month. How many? None. This actually has a probability of 0. And if you have a probability of 0, there's no overlap between a day from the summer and a day from the winter. So because there's no overlap, that addition rule for probability says you add the probabilities, and when you take away the intersection, we're going to take away 0. 9 out of 36 plus 9 out of 36, take away 0 out of 36. We always have to take away the intersection, but if there actually mathematically, numerically, is no intersection, statistically, probabilistically, then we're taking away 0. 9 plus 9, divide by 36. And that is 1/2. Half of the numbers. And that should make sense. Half of your days are summer days. Half of your days are winter days. Half of the days of the calendar are summer or winter, because there's no connection, no intersection between them. So we're able to therefore calculate our probability of choosing a summer or a winter date. And since they have no intersection, we still use the formula, but we're just taking away 0. In fact, that observation lets Gerald say, sorry if you're in my class and I said your name that strongly, but if not, you're fine. Gerald says that because the summer month outcomes and the winter month outcomes are disjoint sets. Disjoint sets are sets with no outcomes in common. A summer and a winter, they have nothing in common. In our calendar, right? Don't go reaching for other stories. The probability that one of the event or the other occurs is just the sum of the probabilities. And it's not necessary to subtract the probability of both events. Is Gerald correct? Yeah. But like, at least acknowledge it. At least acknowledge that there's no intersection and the probability of having no intersection is 0. So like, yeah, but he found a shortcut. Gerald found a shortcut. And I'll put it in quotes. I mean, it's not really even a shortcut. It's just maybe like lazy thinking. Or is it? Okay, I will acknowledge if Gerald says, I am thinking very intelligently about this situation, and I have discovered that disjoint sets have nothing in common, so therefore their intersection and has a 0 probability. And if I acknowledge addition or subtraction by 0, then nothing is ultimately changing through the conversation of subtraction by 0, therefore I'm not going to include it in my formula. Drop the mic. Walk off the stage. You win the day. But I don't think Gerald said that. Wait, what did I say? What do I write here? Yeah, Gerald found a shortcut. It is true that disjoint sets... Oh, there's the bell. Don't pay no attention. You're going to watch this. You're going to be like, LeBrant, why are you still talking here and the video's going? It is... You talked about Gerald and didn't like let yourself wrap up the video for the bell ring. It is true that disjoint sets have 0 intersection. So don't worry about subtracting it. Thank you for watching, like, comment, and subscribing. See you in the next episode.